Alright guys, today we're going to solve this Atwood machine problem. We're going to assume the blocks are already accelerating, which means they're moving, so we can use the coefficient of kinetic friction, which is given to us to be 0.3. So the first step in any Atwood machine problem is to draw free body diagrams of both objects. So, as you can see here, they're already drawn, but I'm going to go through them and explain. So we're going to start with this red block right here. So in the x direction, we're going to assume this is the x direction. It flows this way. We have the tension, which is connected to block 1 and block 2, pulling it this way. And we have the force of kinetic friction diverting it this way, to the left. Now we're going to go in the y direction on this red block. So you have the force normal pushing from the triangle up, and you have the force of gravity pointing straight down right here. Now, since we have an angle right here, we're going to split this up into vectors. So we have the force of gravity in the y direction and the force of gravity in the x direction. We're going to need to solve for those components later, as well as the force of gravity. But we're going to, for now, look at this second block. This second block's a lot easier to look at. You just have the tension coming from this block again, upwards, and then you have the force of gravity downwards. Alright, now it's time to do some basic algebra. So, we need to find the acceleration. The sum of the forces equals mass times acceleration. Specifically, we need to look for the sum of the forces in the x direction, because that's where this system is moving. We define this as the x direction, that's where it's moving. It's not going to start magically floating up in the y direction after all. So to start finding the sum of the forces in the x direction, we're going to need this x component of gravity. So we need to solve for gravity, which is mg. Specifically, we need to solve for fg of x. Now we're going to need to use some basic trig. So we have opposite over hypotenuse, remember this is a right angle, and we can get mg sine of theta after all, so in SOHCAHTOA, mg sine of theta. Now we need to do force of gravity in the y direction. Same thing, basic trig, so you have adjacent hypotenuse, that is ka in SOHCAHTOA, so cosine of theta, and now you have your fg theta component. Now we need to solve for all the forces, the sum of the forces. The sum of the forces in the x direction equals mass times acceleration in the x direction. I guess it'll just be called max here. And that is because the block is moving this way, tension will be the strongest force. So tension minus mg sine of theta, the x gravity component. Let me grab theta really quick. Mg sine of theta minus kinetic friction, which we don't know yet, but we can substitute in later. So f of k equals max. Alright, so we're going to make sure we remember this for later. Highlight it. And we're going to solve for the force normal so we can use it later. Specifically, the components in the y direction. So, the sum of the forces, let me grab my sigma. Sum of the forces in the y direction equals 0. Because the object is not floating in the air, okay? So we have force normal minus mg cosine of theta from fgy. Let me grab my theta. Equals 0. You can throw mg cosine of theta over to this side of the problem, and you can get the force normal equals mg cosine theta. Again, let me unbold all of this really quick. It's bothering me. Alright. We're going to keep this in our equation holster and use it later. So this is all for red block. Now we're going to go to blue. Gosh dang it. Blue block. Alright, so blue block's only got one way to move. In the x direction, it's only got forces in the x direction, so sum of the forces in the x direction is going to equal max. So specifically, if the block is accelerating, that means it's moving downward, which means the force of gravity is going to be greater, and you're going to subtract that from tension, and that equals max, which is ma in the x direction. So we're going to highlight and bold all these important formulas. Alright, so now that I've cleaned up our equation holster and the rest of our work, we can finally solve, or attempt to solve, for the final acceleration. So here we have a lot of unknowns. We don't know kinetic friction, we don't know tension, we don't really know force normal either. So what we're going to do is we're going to bring this formula down because it has most of what we need to solve the problem. So we're going to start with our kinetic friction. How are we going to find that unknown? Well, if you remember, the force of kinetic friction equals, let me grab my mu, it equals mu times force normal, which, using our previous equation holster, we can get to be Fk equals mu. Let me fix that font size. And then we can use our previous equation to equal mg cosine theta. So now this equation turns out to be T equals mg sine theta minus u mg cosine theta equals max. So now we need to find a way to get to tension. Luckily, we have a formula for that. We need to solve this formula, mg minus t equals max, mg minus t equals max, and we need to solve that for force of tension. And we can solve that to be t equals negative max plus mg. So plug this puppy into our previous formula, and you'll, oops, and you'll have a lot of m's for one. So now we have a lot of things that we may actually know how to solve for. We have max, mg, mg, lots of mg's. So what we want to do here is we want to get rid of all the masses because every single variable here has mass. So everyone brought mass to the party after all. We can get rid of all the m's. Let's get rid of all these. And that makes the final equation look a lot more presentable. But we can start by adding a acceleration in the x direction to both sides, which would give us 2ax equals this. And there's a g in each one of these, so we can factor out a g. So we can get g my mind blanked, sine of theta, copy this theta, minus mu cosine of theta. All of that equal to 2ax. Okay. Now the question is, what do you do? Now we can plug in everything because we know all of these values. The only thing we don't know here is acceleration. We know gravity. We know sine of theta because theta is 25 given to us right here. And we know the coefficient of friction, 0.3. Yes, 0.3. So you could plug all those numbers in. And that'll give us 2ax equals, we're going to use 10 as gravity because it makes our numbers a lot prettier. Sine of 25 minus 0.3 cosine of 25. Alright, before wrapping up this problem, I do want to point out one thing. As you could see, in this right here, we have mass everywhere, but then we could cancel everything out, which means Mass does not affect the acceleration of this problem. All right? It eventually cancels out. So we have this final equation, and I have just calculated this side of the equation to be 3.1. So 2ax equals 3.1 divided by 2 to get rid of both. And our final acceleration is 1.53. 1.53. In the x direction, of course. The acceleration in the x direction is 1.53. So what does that mean? That means the acceleration moving block 1, or the red block, over here is 1.53 meters per second squared. Just going to give you guys a quick summary of everything we did here. We drew the force diagram of both the red block and the blue block. We solved for the force of gravity. We solved for the forces, some of the forces in the x direction and the forces in the y direction, so we could get two of these equations. Then we did the same thing on the blue block, sum the forces in the x direction. Remember, the x direction is to the right of this red block, so this way. It's kind of weird, I know. And we got our third equation in our equation holster. Then we took this first equation, used it here, solved for the coefficient, or solved for kinetic friction using the coefficient of friction formula. We plugged it into here, got this equation from our equation holster, solved it for t, plugged it again into here, and then we condensed this big formula into just this and solved for our acceleration, which was 1.53 meters per second squared. Thank you everyone for watching, and I hope you have a great day.